Alright, so today is 4.3b, which is connecting the graphs of the derivatives to the function. We already started with this in A. So today we're specifically going to be talking about something called concavity. So the second derivative test helps us find something called concavity, which is the shape of the curve, and the points of inflection, which is where the concavity changes. So you were used to looking at extreme values or critical points with the first derivative. The second derivative version of that is called an inflection point. So make sure you don't confuse the terminology of an inflection point. We know inflection point is specifically reserved for the second derivative, and concavity is always second derivative. So essentially, if the second derivative can be found to be greater than 0 at any point, then we know that it is concave up, and then concave down if it is less than 0. So this is what concave upward looks like. Okay, it's kind of like how you can say like a quadratic is concave upward, okay, 'cause it's pointing up, and then a negative one would be downward. The main, the actual, mathematical definition of concavity to determine if something's concave up or down is actually dealing with its tangent lines. So we know that any graph has an infinite amount of tangent lines. Basically, you can put a tangent line at any of the given specific spots with the slope. Something is always concave upward if you were to draw a tangent line on it, and the tangent line would fall underneath the graph, okay? Now, if something is concave downward, what do you think about the tangent line here?
Be above.
It's always above. All the tangent lines would always be above the graph. So that's how you can determine if something is concave upward versus downward just visually. So here's some other examples of concave up and concave down that might be a little less obvious to notice. So concave upward can occur when we have a tangent line that switches direction. So if we drew a tangent line here, it would be below here but above over here. And then we have this, which is called a vertical tangent line. A horizontal tangent line, where we change from concave downward to concave upward. And then what do we call this one? Vertical tangent, which we also switch from concave up to concave down. And then here's a few more drawings to show you what it looks like with the vertical with the tangent lines that you can see here. Concave up is below, concave down is above. Alright, here are the steps. You can use these as a reference point if you ever forget what the steps are. They're on your notes. So I'm just going to go through these as we go through the steps of the process here. Yeah, I know. It's because I had the stapler myself, so.
Girl,
yeah.
Girl, it looks like I'm making a paper airplane the way you do it. Yeah.
You guys can rip it apart if you want. It's up to you. Okay. So, step 1 is going to be to take the first derivative. So you're going to start by taking the first derivative of the function, which is going to look like this. And then step 2 is to take the second derivative from the first derivative. So now we're taking the derivative of the first derivative, which will come out to be 60x cubed minus 30x.
Word.
Once you have the second derivative, you're going to set it equal to 0. And then your goal from here is to solve for x. So of course we want to factor out a GCF if we have one, which is what here? 30x. 30x. We're going to take out 30x, and that's going to give me 2x squared minus 1. Good. Then you're going to set each of these products equal to 0 on their own. Like this. And then this one, of course, is just going to be x equals 0. But over here, I'm going to add 1 to both sides. And then I'm going to divide by 2. And then what can I do to get rid of the square? We take the square root. Now here's the important part. It would be plus or minus 1 over the square root of 2, because you can take the square root of 1. Yeah. So the main important part is to make sure you have the plus or minus. Because what will happen is if you miss one of the inflection points, your whole little number line is going to be messed up, right? Because then if you're everything to the left, you might get the wrong symbol, so everything just gets messed up. So make sure when you take square root, you know you have a plus or minus. So x is approximately equal to 0.7 and negative 0.7. Everybody know how I got that? I just put this in the calculator, and we have a negative positive version of it. So those are the approximate values rounded to the nearest tenths. So now that I have my inflection points and the approximations, I'm going to draw my little number line thing.
So it's the same thing as the last lesson.
Similarly, but a little bit different because they mean different things, and how we analyze it is different. So this is 0. This is negative 0.7 and positive 0.7. And then I just want to remind everybody why it's useful in this particular case. This right here is going to negative infinity, and this over here is like positive infinity, okay? So keep that in mind. It's basically a whole number line, okay? So if we determine something is negative here, that means it's going to be concave down all the way from negative infinity to negative 0.7. So just, I want to make sure you are aware it's a full number line with every number on it.
In this case, it doesn't have the limits.
Correct.
Yeah.
Anytime that we're not given an how do you say it? Yeah, or in a range or values, right?
You're implied that it's going on forever in that direction.
Exactly. Exactly. So what's a number I can plug in that's less than 0.7?
Negative 1.
Yeah, negative 1. Now keep in mind, you can choose to plug it into the pre-factored or the factored version, whatever one you think is going to be easier for you to do. So either one would be technically correct. Just be aware of that. So we get a negative 60 plus 30. Is that going to be positive or negative?
It's gonna be negative.
It's going to be negative. What can we plug in between negative 0.7 and 0? Yeah, negative 0.5, right, would work.
That's fine because it halves everything, right? Or like it can like.
It's easier to deal with like numbers that are easier, but of course like anything would work. You could do like negative 0.1 if you wanted to.
Yeah.
So I'm going to put this in my calculator because it's just easier for me to do the math that way. And it actually comes out to be a positive 7.5.
Ew. Ow.
Yeah, how?
If you put it in the calculator, it comes out to be positive.
Because a negative, because that's going to still be negative.
It's still going to be negative, but this is going to be a bigger number, so it's going to be a negative plus a bigger positive, which is a positive.
Negative 30.
Maybe you
times
got
1
30,
half,
30,
60
and now you
times
got
1 half.
15 because 30 times.
This is going to be plus 15. This is going to be negative 7.5. So this is going to come out to be...
Oh, because it's negative and negative. We didn't look at the negative.
I didn't see. I forgot the power of 3.
Oh, okay. Yeah,
So
the
it's
power of
positive.
3 keeps something negative still.
I just thought, yeah,
No, power of
I
3 is
see.
small. That's the problem.
So if you plug in regular 0.5, it's going to be a similar situation, but instead this part right here is going to be smaller and this is going to be bigger, so it's actually going to be negative here. And if you don't believe me, feel free to test it out. And then if we plug in regular 1, it's like this but with a regular 1. So that's going to end up being just 60 plus 30, which is, or 60 minus 30, which is still positive. So we have positive, negative, positive, negative. How we analyze it is different than with,
I mean, negative, positive.
yeah. So how we analyze it is going to be different than how we do with the first derivative. Because remember with the first derivative, these right here can be maxes and mins. This is different. This is saying that everywhere over here is concave down. Everything in this interval is what?
Concave about.
Concave up. Everything here is once again concave down. And everything over here is concave up.
It's fun.
So these right here are what we call the inflection points. So these are where things change from concave up to concave down. They're not necessarily maxes or mins or anything like that. They are inflection points. And you can see what some of the inflection points look like on all those pictures on your notes. So if they ask for inflection points, that's how you find inflection points. You set the second derivative equal to 0 and solve. So we're going to look at the Desmos graph real quick. So as you can see, I gave you the regular graph, but notice that the vertical lines I put on here indicate your inflection points. Everybody see that? So do you see how over here everything over here is concave down? Everything in between the black and the green is concave up, and then here it's
Down.
and then it's up again. So if you want to add these lines onto your graph to indicate where the concavity changes, or you want to mark where the inflection points are, that might be useful on your notes because you have that little graph on there. And if you don't want to put the line, you can probably just put like a little point, a little dot at where they are. It's just hard to do that on here. It's harder to do it on this graph, so I just put lines. But does anybody have any questions about the graph? Does everybody understand how the inflection point's up here? Okay. So today we